Our Penn State Systems Lab course culminated with a Jetbot programming project. It was free-form, it was multifaceted, it was challenging. 3 weeks long, 3 separate labs, followed by a final lab that brought all of them together, and a little more. By the end, we'd brought together fundamentals from dynamic systems, pathfinding algorithms, bot-to-bot communication, and a whole lot of Python. The general goal? Make the robot move somewhere we wanted it to, in the way we wanted it to.
Before we could focus on the end goal task of the Autonomous Vehicles Lab, we had to get acquainted with the Jetbots and how they function. Week 1's lab was focused on the basic controls for the Jetbots and getting used to kinematics to control velocities. We were able to get accustomed to the Python interface from Jupyter Labs and communicate with the robots via IP addresses and utilizing the kernels. Code was organized and pre-designed to make it for easy to understand controls. This was a key aspect to the rest of the process, as Python and kinematics would be the base for the following weeks of development. Week 2's lab had us utilizing image processing and deep learning software to allow for input commands of different situations. This allowed for more possibilities instead of being stuck on a set program. Utilizing Jupyter Labs' preset kernels, we were able to successfully upload a live feed from our Jetbot's camera. Using this live feed would allow us to attempt line following programs. First, we had to adjust the HSV, hue, saturation, and value values, to create a clear distinction between the road, the white sidelines, and the yellow lines meant to be followed. Once we had a clear distinction, we had to allow for the PID controller to make changes to our robot's drive system so that it was stable. Adjusting the P&D gains took time and was a trial and error process, but eventually Jetbot 11 was able to drive in a straight line and follow the yellow markings. Now was the deep learning aspect. In order to train a model to successfully identify stop, speed limit, and none, we took an average of around 40 images for each situation and labeled it as such, thus allowing for differentiation between all 3 criteria. Our model had then been trained to 0.98 accuracy, which was right every time we tested it. Week 3 was where we took a step into the robot-to-robot communication. We first connected to the camera bot within the lab to allow us to communicate with our individual Jetbots. From there, we took a picture of the map from above and collected images with the distortion grids in order to collect a matrix and correct the image. With the now corrected image, we were able to take a new picture with our Jetbot on the map, and with the April tag visible, this allowed the camera bot to scan and recognize the location of our Jetbot in real time. Once this was complete, we dove into path planning. We took a similar image to that of before, but now the Jetbot was absent. Once this image was taken, we adjusted the intensity until the road and non-road aspects of the image were completed, distinguished in white and black respectively. Then we set a desired end location and adjusted the nodes, node length, and the times in order to have the smallest path possible set. Utilizing all 3 of these labs will allow us to collectively complete the ultimate goal of letting our Jetbot autonomously go from point A to point B in the shortest distance possible while following a path and identifying signs.
Our team-defined task was to make the Jetbot move to a desired location and follow the yellow line in the road after reaching said location. The team aimed to make the robot complete a turn and then follow the line. Additionally, the team desired to retrieve the initial position of the robot. The robot's initial position was retrieved by using the connected camera bot to recognize the April tag. Inverse kinematics was used to move to the turn, take the turn, and drive straight for 4 seconds. It then used path following to continue following the yellow line. Although this demonstration is basic, inverse kinematics could be used to time the line following and perform more moves to complete a more difficult task. Overall, we didn't just demonstrate the team's ability to complete this simple objective, but to show how knowledge from the labs can be used to complete other more difficult tasks.
As you can see, there are multiple parts here. We've decided as a team to divide each sub-project, sub-program into its own setup in order to create an easier way of understanding. However, the main objective will be that of the center. To start off, we're going to take a look at the start of the setting up the April tag location, as that's one of the most important ones that you can do before the robot actually does anything, movement-wise. So through here, we're going to create a connection to the Jetbot, a connection to the camera bot. We're going to insert a map as a JPEG with the Jetbot present. Then we're going to collect the camera matrix and distortion grid images to create the coefficient for the camera. This will then allow us to communicate with the camera bot to find the location of the April tag and output the live robot location. This is the created and final sub-program of the robot location and communication. So that is now done. This acts as one of the 3 inputs to get to our path planning. So up here we start. Our first input is the pixel to life scale, which relates to the second input of the map image to a JPEG. And then our third input, as previously mentioned, is the robot current location and end goal position. These 3 together create the sub-program of path planning. As you can see, path planning will then have an input of the robot current location and end goal position once again, thus reiterating its goal. Now, before we use the kinematics to move the Jetbot to the next node, we have to actually set up our basic controls as well as our path following. So over here, our basic controls, we have our start with our inputs of motor speeds and time. Under motor speeds, we have the process of getting kinematics to get velocity values. Combining that process with our input of time, we get experimental motor values using the equations to set up our final basic controls. This will tie into the path planning as well as our path following. To set up our path following, we get an input of a live video feed. We input HSV, which is hue, saturation, and value values. This decision, are the lines clear? If the lines are not clear, redo the HSV values until they are. Once they are clear, you will input a PID controller equation, which will allow for 2 processes, collecting images to train the deep learning, which we will come back to later. The decision here is to make sure that the accuracy is above 0.85 with its decision making. Once that is done, your deep learning is set up. However, what we were focusing on is adjusting the PND gains to create stability. The decision here is it stable? If it's not, keep going, adjusting those PND gains to create stability. Once it is stable, you will have created your path following sub-program. We will combine path following, basic controls, and path planning to use kinematics to move the Jetbot to the next node. The next node will then activate the decision, where is it? You will have 2 inputs, either the live location at an intersection or a live location at a straight. If it's at a straight, the decision will be the process of straight using basic controls. If it's at an intersection, you will have the decision left, right, or straight using those basic controls. Both of these will meet again at the input of the sign. The decision will be what sign? That will be assisted by the deep learning subprogram, which will input the sign command. So depending on what sign it scans using the deep learning, it will have the output of decision left, right, or straight. Once that is decided, it will input once again the live location using the April tag, which is part of the April tag communication. If it is still on the path process, it will go through the location loop again and again until it is at the end goal location, in which it will end. Goal achieved.
This team has really excelled over the course of the last month and has personally grown to become my favorite team and my most talented students. They achieved their goals in a timely manner.
Thank you for the kind words, Tomas. To pick up where he left off, our group was committed to demonstrating our improvement in understanding of kinematics, Python, and the overall behavior of the Jetbot that, in the end, went where we wanted it to go. Thank you.